We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
Very happy to be here today to talk about a topic that's very near and dear to my heart, which is the role of technology in human evolution. In fact, if you go back about 60 years, it was pretty much widespread viewpoint that technology and tool-making was absolutely central to human evolution, and in fact, perhaps definitive of our species. This was graphically represented in a film in 1968, 2001, A Space Odyssey, which depicts this turning point, a critical turning point in human evolution, when this Australopithecine, male of course, realizes that he can use a bone as a club and then proceeds to slaughter his rivals with it. From then, our future was assured and virtually inevitable. In triumph, he tosses the stone up in the air. It spins around, and then on the way back down, it very smoothly, at least in 1960s cinematography, turns into a spaceship. So you get the picture, right? But already by the time that this film had come out, and you saw this quote in the last presentation, this vision of man the toolmaker had started to unravel a bit, as Leakey famously quipped, now we must redefine man, redefine tool, or accept chimpanzees as human. And in fact, now we know it's not just the chimpanzees, it's not even just the primates. If you're willing to accept kind of covering yourself with a coconut as tool use, it goes into mollusks even using tools. And as archaeologists, we also know that the earliest appearance of flakestone tools was not really a transformative breakthrough that we thought. The first stone tools appear around 3.3 million years, and then nothing happens. In fact, the graph should probably look more like this. You have a little bit of a flash or a flash in the pan. Let me get the laser pointer up here. At 3.3 million years ago, then a whole lot and nothing. Until about 2.6, where you have some low-intensity mucking about in tool-making, but it doesn't really take off until after 2 million years. So maybe early stone tools really aren't that much of a big deal after all. But obviously, I don't believe that. And in fact, you could say that the termite probe here is a tool, the phone is a tool. They're the same thing qualitatively, but quantitatively, there's a massive difference in complexity that we need to explain. So take this famous scene from the Shibuya crossing in Tokyo. Arguably, there's not a single natural thing in sight here. Even the people, even the bodies, the human bodies have been transformed by this long engagement with technology. The reduction in the size of our jaws and teeth and our gut from external processing of food, the adaptations to the hand and arm for dexterous manipulation, and of course the very large energy-hungry brain. But the other thing to notice in this picture is how many people there are. Despite this really expensive brain, the very long development, the heavy investment that children require, if you may be familiar with, there's more than 7 billion of us on the planet. Compared to the other apes, human mothers have the shortest interbirth interval and the highest total fertility rate, despite having these really expensive offspring. So basically, they should not be able to afford to do this. Human women should not be able to afford this rate of reproduction. So how do they do it is they do receive assistance from others. This could be fathers, could be siblings, could be grandparents, other members of the community, and a strategy that's been called a human biocultural reproductive strategy. But obviously, for these other individuals to provide assistance to human mothers, they have to produce more than just what they themselves need to survive. Right? And throughout the life course, chimpanzees pretty much produce what they consume and consume what they produce, except for maybe a little bit of nursing right here at the outset. It tracks closely. Now, humans, we have this long, very expensive childhood in which we are producing much less than we're consuming. But eventually, we're able to start producing a surplus. And the reason for this is what I call technology, these culturally inherited, passed on techniques for exploiting the environment. Right? So this describes a human technological niche. What you've got here is a powerful biocultural feedback cycle where technology can increase production, which provides the resources for sharing, which can subsidize long, expensive development and population growth, which makes it possible to grow and educate a large brain, which makes it possible to have further technological innovations, and so forth. Now, as I articulated there, this suggests a very powerful, as I said, feedback, or even a runaway feedback curve. So maybe we're back to the guy tossing the bone in the air after all. Once it gets started, how do you stop it? But in fact, not every technological innovation is necessarily going to be a game changer that is going to increase your production. Increase in intelligence may lead to greater refinement of tool making rather than some kind of innovation. And so models that take the interaction between some of these variables into account, well, they can produce this exponential curve, but they can also produce a series of steps and plateaus that's a lot more like what the archaeological record actually looks like. Right? So unfortunately, things are complicated. Life is complicated, and we have to turn to the actual archaeological record and try to figure out what happened, when, where, and why. So why didn't the earliest stone tools take off? Why wasn't this a game changer? Right? So if you've ever loosened or tightened a screw using the knife you happen to have in your hand rather than digging through your tool chest to get a proper screwdriver, or if you've weighed the costs and benefits of updating your operating system, you know that the technology, it comes with both costs and benefits. So for instance, technology might increase your rate of return, but before you can start employing it, you may have to gather raw materials, you may have to actually produce and maintain the tools, and critically, you've got to learn how to do all of these things before you can even start harvesting from the environment. And in some circumstances, you'd be better off to just start right in with a simpler technology rather than wasting all of this time. I'm going to focus, the argument here, to make it explicit, is that this could help to explain some of the patterning that we see in the archaeological record. And I'm going to focus in particular on skill learning, the cost of skill learning, because this is something that evolutionarily, brain evolution could mitigate the costs of skill learning, and also changes in our donation of time and energy in the form of teaching. So sharing our time and energy to teach others could alter the costs and benefits of skill investment in skill learning. All right, so chimpanzees, apes, can make stone tools, but they don't do it in the wild. And in fact, it takes them a really long time to learn how to do it and how to make tools that are frankly not very good. So it's really no wonder that they don't bother to do this. Now, part of the reason, and Dr. Ferghese talked about some of this, part of the reason is probably has to do with their hands. So they have these very long fingers that make some of the manipulations of stones that we do for stone tool making difficult. But I think that there's more to it than just the hands. All right, so for reference, here is a skilled modern human making simple stone flakes. These sharp pieces of rock that are coming off are surprisingly effective knives. Actually, you can use them to butcher a wide range of animals. And what's required here is to identify the appropriate geometry on the stone, to very dexterously manipulate and support it with the left hand while delivering very forceful and accurate strikes with the right hand. Now, this is not rocket science, but it does require some pretty sophisticated spatial relationships as well as some highly skilled manual movements and control. All right, so I don't think it's just the fingers, but I think it's also the brain that's involved here that makes this easier for humans than it is for chimpanzees. And in fact, humans have a expanded neural system, a dorsal stream for relating things like spatial relations, body positions, object identification, and kinematics to technological goals. That I think makes it easier and less costly for humans to learn these kinds of skills. And in fact, this is exactly, and if you do a functional imaging of the systems that are activated during simple stone tool making, this is the same network of structures that you see involved there. All right, so if we turn to Australopithecines with their small brains, with large jaws and teeth and guts adapted for digesting unprocessed kinds of foods, with hands and arms that may or may not have been up to the task, it's probably the case that stone tool making just wasn't really worth it for them as an investment. The exception then that proves the rule here is the Lemequian stone tool making, which actually is produced using less demanding techniques like indirect percussion against a rock, a stationary rock like this, or bipolar shattering on an anvil. And you can see that the experimenter here actually has their fingers bound together to make this point. It requires a lot less demanding kind of manipulation. So less investment in skill, but perhaps also less payoff in terms of the effectiveness of the technology. By 2.6 million years ago, we do have evidence of more skill-intensive, more dexterous freehand flaking, like what we saw in that video from the site of Gona in Ethiopia, where I work with Dr. Seleshi Sema. And you can see some of these tools are made very finely, very small, some very delicate flaking and precise gestures involved there, and arguably then could be a more efficient technology that might have a better payoff. We don't really know very much about early Homo that was around at this time, except the teeth maybe are a little bit smaller. We could speculate the brain's also bigger, but we don't know. Australopithecines also around at the right time and place to make these tools don't show any obvious adaptations for tool making. And the sites on the landscape remain rare and somewhat ephemeral, and so this is maybe sometimes worth it. And it's only after about 2 million years ago that we see what I'm going to loosely call habitual tool making, habitual old one tool making. I think John Shea, who we'll hear about from, has a different definition of habitual, but I just mean in the sense that they're doing it much more frequently. The sites are larger, they are denser, they occur across more of the continent, it persists. And this is interesting because there's a pretty loose, we like to do these correspondences between this shift in the technology and the appearance of evidence of larger brain and body size. And it's pretty rapidly after that, by 1.8, 1.7 million years ago, that we see the invention of an entirely new technology, this we call the early Acheulean, where for the first time tools are being made to an intentional shape, imposing a point, these things we call picks, and hand axes, which are often made by striking a really large flake off of a boulder core, which requires a whole different technique and different kind of manual skill, and seems to go hand in hand with the appearance of Homo erectus in the loose sense, with larger brains and body size. This then appears to be a fairly stable adaptation. With or without hand axe, hominids are able to inhabit diverse environments throughout Eurasia, even up to the edge of the boreal zone here. And in places where hand axes were made consistently, like throughout this period, like in East Africa, there is some evidence of incremental refinement, but overall things seem to be pretty stable, if variable, stable but variable for about 1 million years or more. And it's by then about 500,000 years ago that we see clear evidence that we've entered into another sort of period of abrupt change indicated by rapid encephalization, by the expansion into new habitats, and by the appearance of new forms of technology as well. And one of these that I've studied in some detail are Latitulian-style hand axes, like this one from Boxgrove in the UK. And in contrast to earlier tools, earlier hand axes, these are very nicely shaped and especially made very flat and thin in cross-section. And I emphasize that because that's actually a very difficult thing to achieve with a rock, by hitting it with another rock. You start off with a big nodule, irregularly shaped, and you have to flatten that thing down. And the only way you're going to be able to do that is if you can strike flakes that travel more than halfway across the surface of the rock. And to enable that kind of fracture, you really need to be able to delicately adjust the angle, the placement, and the bevel of the edge relative to the midline in order to ensure that the flake you strike is going to actually travel some distance along the core face. Archaeologists call this striking platform preparation. And this entire technology is a very demanding one. So in order to find out a little bit more about exactly what goes into learning how to do this, we recently ran an experiment training modern people to make these kinds of stone tools. About 20 people. They received close to 100 hours of training, each from an expert stone toolmaker, Dr. Nada Krisha, their products, and we've collected all kinds of information about these people and their behavior. Their lithic products I'll talk about, the actual tools they made, have been analyzed by Dr. Justin Pargeter in my lab as well. He's my current postdoc. And what we found is a classic power learning curve in which early progress is rapid, but then it asymptotes off to pretty much a plateau, diminishing returns from practice. You may be familiar with this kind of effect in sports or anything like that. It's found across a wide range of different skills. Things being as they are in life, although we tried to control training time, there was some variability in how often people were able to make it into the lab for training sessions. And we found that not only is it the total amount of practice that you've racked up, but it's actually the density, the frequency and intensity of your practice that helps to determine individual differences in the progress of skill learning. I want to point out here that this scale is actually a 5-point scale, so the top is not even being shown on the graph because nobody even got close to it in 90 hours. We could extrapolate from individual learning curves. The people in our study we expect would have taken anywhere from 121 hours to over 400 hours to achieve mastery comparable to what we see at Boxgrove in this kind of tool making. This is a very substantial investment of time, especially considering that we've given these people everything. They don't have to gather their tools, don't have to make their equipment. It's all right there for them. And we're still talking several hundred hours of dedicated practice. And this, to us, begins to suggest that we may be starting to see some of the kinds of support that modern humans provide for the transmission of complex technical skills, everything ranging from intentional demonstration, perhaps explicit teaching, certainly social support, coaching, scaffolding, and encouragement. Right? So the social context, a very important part of what's evolving here in the technological niche. The other thing, of course, is that learning complex skills does require complex cognition. And during this initial jump in performance here, we found that individual differences in how rapidly you kind of learned this skill were related to your performance on a classic neuropsychological test of set shifting. Basically, you have to match this card to one of these. You can match either on shape or color or number, and your ability to do that, they keep changing the rules. Your ability to recognize when a rule is changed is your set shifting ability. And if you temporarily mess with the part of the brain that controls this in the right inferior frontal gyrus with a magnetic pulse, it slows people down in being able to put together complex action sequences. Not coincidentally, this very same part of the brain is what we consistently find to be active in studies, functional imaging studies of people making stone tools. It also experiences changes in white matter connectivity during training. In fact, these changes are paralleled by species differences between humans and chimpanzees, in particular the right hemisphere inferior frontal gyrus. So we can say that evolutionary changes to this system in humans parallel the effects of tool-making training. The remaining question is, whether this is genetic adaptation to tool-making ability, or whether it's the developmental context of growing up in a technological niche, or some combination of those two, which is obviously the most likely thing. Anyway, it's going to be complicated, but hopefully by continued study of the archaeological record and focused experimentation, we can begin to sort out some of these details of the very extended and multi-stage process through which the modern human technological niche evolved. Thank you.